There's a lot of chemicals out in the environment that we really just don't know much about, and we need faster, more efficient ways to just learn more about how they affect human biology. So the assays that I run in my laboratory are designed to cast a broad net, to look at many different aspects of biology all at the same time. We can then pass that information along to state, local, and federal stakeholders to help them inform their decision-making process on how to protect the public health and the environment. My name is Josh Harrill, and I'm a toxicologist at US EPA's National Center for Computational Toxicology. So prior to coming to EPA, I was what you call an emergency response toxicologist. And so my role in that job was when events happened that involved the release or the threat of release of chemicals like a factory fire or an oil spill or a train derailment or things like that. My job was to come up with sampling analysis plans where we rapidly collect data regarding the chemicals that are in the air, the water, and the soil surrounding these disaster sites. Oftentimes when you're in these emergency situations and you go out into the great unknown, you can encounter chemicals that are also equally unknown. I run what is called a chemical screening laboratory. So that is a laboratory where we can rapidly test thousands and thousands of chemicals for their biological activities in human cells. Traditionally, when you wanted to get information on the toxicity or hazard associated with a chemical, you ran animal testing studies. To do this comprehensively, it can often take years and years, thousands if not millions of dollars. As an alternative, what we do is we test chemicals in cell cultures and can test much more rapidly and efficiently at lower costs. The way that this process works is we have what are called culture plates, and these are little pieces of plastic that have individual chambers in them that we call wells. So what you can do is take some cells, culture them in each of these little compartments or each of these wells, and then apply your test chemical to those cultures and observe how the cells react. And we can also use human cells instead of using animal cells, so it's more relevant to human biology. The assumptions that we're working under is that human cells that are actually derived from human beings will reflect the biology that's present in you and me better than a rat or a mouse. We look at a broad array of chemicals, so from many different use types and many different sectors. So we look at pesticides, solvents, industrial chemicals. TSCA is a piece of legislation known as the Toxic Substances Control Act. It mandates that EPA regulate chemicals. That's not a simple mandate. There are many, many, many chemicals in the environment. So one of the things that the data we generate can be used for is to help prioritize which chemicals we should look at first and which should be prioritized for maybe greater resources. The data also can be used in a different context, so as far as cleaning up contaminated sites. Often you'll come across a contaminated site and you may encounter a chemical you don't know a whole lot about. So likewise, our data can help fill data gaps. If we have a chemical that's data poor that we don't know a lot about, and we see a particular profile in our assays, and that profile looks very much like a chemical we do know a lot about, then you could use the information from that chemical as a surrogate, whether that's in an emergency response situation or kind of a slower time frame cleanup. I know the kind of frustrations that people can have and the kind of anxiety it can cause to not know a lot about the chemicals that you're dealing with. So this job provides me the opportunity to help solve that problem and really carry back with me this real world experience to help generate some of the information we need to effectively protect the environment and protect human health.